Wait, is this all?
Crazy, man. It was pretty, I think it was being fairly simple. It seemed a bit harder. Yeah, A is just the then B is just O equals and then C is just A equals pi with B. And then you just gotta explain that, oh.
I was starting.
That sounds a lot easier than I figured like my
Oh, I have a motor. That's crazy. Mine is not the razor. Mine is a motor. I also.
All right, good afternoon, everyone. So I hope you're doing well. What I want to do today is I want to finish off the preview of Lab 3, which you'll do tomorrow. And then we'll actually discuss what you'll do in Lab number 4 next week. Lab number 4 is actually one of our labs that will span 2 weeks. So you'll do Lab 3 tomorrow, and then you'll hand it in a week from tomorrow when you start Lab 4. But Lab 4 will span 2 weeks, so for that one, you won't hand in your lab books until 2 weeks after the start of the 4th lab. So the goal for today is to preview lab 3 and then also start to think about what you're going to do in the first part of lab 4, 2 weeks from tomorrow. All right, so in lab 3, you're going to study the series RC circuit. And the idea is that we're going to have a battery that we can either include in the circuit by flipping the switch up or remove by flipping the switch down. Now, you're not actually going to have a physical switch when you do your experiment tomorrow. So instead, what we'll do is we'll use the TTL output of the function generator, which outputs a square wave that goes 5 to 0 to 5 back to 0. And the idea is when the output of the function generator is 5 volts, then that's like we have the battery in the circuit and the capacitor starts charging. When the output of the TTL is 0, that's like connecting this terminal directly to ground. And so if you have a charged capacitor, it'll discharge through the resistor and the battery is not part of the circuit. And so we talked about how a capacitor charges with time. It was some maximum voltage you're going to reach after a long time, times 1 minus e to the minus t over tau. So you can see if I put t equals 0, then I get e to the 0, which is 1. 1 minus 1 is 0. So we're going to start at 0 volts. And if I say t is really large, I have e to the minus a large number, which is 0. And so the capacitor voltage approaches this V naught. Yeah.
Does the square wave make a difference in the graph of the chart? Like if it was a like sinusoidal wave.
Yeah, then it would be different. Yeah. Yeah. So we will actually talk about the behavior of circuits when we drive them with sine waves. So you'll get a different behavior when you do that. Now, what will happen is if we want this capacitor to fully charge to its maximum voltage, we have to give it sufficient time to do that. And the way you can do that is by adjusting the period of the square wave. So the square wave, this is its period. So if I don't give it enough time, what I could do is turn the frequency down so that the period of the square wave increases, and so it has more time to charge up. And then when the capacitor discharges, it starts from some maximum voltage and then exponentially decays as V naught e to the minus t over tau. Okay, so in lab number 3, we will focus on the discharge of the capacitor such that the voltage across the capacitor is equal to some maximum times e to the minus t over tau. And so the goal of this first measurement is to determine, or let's say to make a quick estimate of tau. Okay, so if we were to think about this plot, and here I'm going to redraw this plot, but I'm only going to draw the discharge of the capacitor. So this is during discharge. And we'll start from some maximum, which will be V naught, and then we'll look at this exponential decay. So what I want to do is I want to think about what happens if we set t equal to tau. So at a time t equals tau, we have the voltage across capacitor when t equals tau is equal to V naught e to the minus. So e to the minus t, but now we're going to set t to be the special time tau, the so-called decay time constant. And then it's divided by tau, and that's just equal to V naught over E, which I wrote down the number today. 1 over E is 0.368 times V naught. So it's about 37% of the maximum voltage. So what you're going to do in the lab is set up your scope to observe discharge of the capacitor. So that's step 1. And then step 2 will be to use the cursors to measure the value of this maximum voltage of the capacitor. So we're going to measure V naught, the max voltage across the capacitor after it's been fully charged. So step 3 will be to calculate, let's say calculate and then find V naught over E, which is going to be that 37%. So let's imagine we did that. So, you know, if V naught is 5 volts or something like that, then 37% of 5 volts would be, I don't know, I guess it would be half of 37, whatever that is. So 18 and a half maybe. So it's something like 1.85 volts. And so you would go over here on your graph and you would say, all right, here is that voltage. This is V naught over E. And so the time that it takes to go from fully charged to V naught over E is an estimate of tau. And so this time range here is tau. So we're going to estimate tau plus or minus delta tau by finding the time required for your capacitor to discharge from V naught to V naught over E. Okay, good. So that's the first part of lab number 3. And this is meant to be a pretty quick measurement. So what I would expect is that you probably wrap up all of part 1 of the lab within the first hour, and then that gives you 2 hours to complete lab number 2. Part 2 of the lab. Part 2 lab, 2 hours is way more than you need to collect the data for part 2. But in part 2, there's a Jupyter notebook where you'll enter your data and do some analysis, some fitting. So we'll talk about that tomorrow when the lab starts, but this is what you're going to start with. Does that make sense? Does anyone have any questions? All right, yeah, go ahead.
Does it mean we should look for tau and then I'm going to compare it with the value we get if we're calculating for
Yep. So you'll also, tau is expected to be R times C. So if you know R and C in your circuit, then you can calculate tau and then compare it to the value that you measure.
Yeah, using the value of the capacitor.
Yep. So you'll know the value of the capacitor and the resistor. Yeah, that's right. Good. Okay, so what I want to do is I want to switch gears a little bit, and I want to just think back to something that we've already talked about, and that was this comparison between a mass on a spring in some kind of fluid and our LRC circuit, which we drew as a series inductor, resistor, and capacitor. And then we drew this kind of switch thing similar to what we just used for our RC circuit here. So here's V naught plus and minus, like so. Okay, so when we analyzed the LRC circuit, we ended up writing down a differential equation that looked like the following. So we previously found, what was it? It was V naught over L is equal to 2 time derivatives of the charge plus R over L dq dt plus Q over LC. And then we found Q equilibrium was equal to C times V naught. And remember, the way we did that is we said, well, once we reach equilibrium, the charge will no longer be changing on the capacitor. So it's constant, dq dt is 0, d2q dt2 is also 0. You set these things equal to 0, solve for the charge, and then you get C times V naught because the L's cancel. Okay, we did the same thing for the mass on the spring, and we found an analogous differential equation that looked like this, where M is the mass, K is the stiffness of the spring, X is just the position of the mass, and B was this drag coefficient. So it's like, it's sort of analogous to the resistance in an LRC circuit. And then we could do the same thing. We could find an X equilibrium was equal to mg over K. The reason we did this analogy was because I wanted to try to convince you that even though these are complicated differential equations that we didn't solve and we're not going to solve because you'll do them next term, we already knew what to expect from the behavior of the system. It should be, I pull the mass down and I release it, it starts to oscillate, but because it's moving through a fluid, it has some drag, and so the amplitude of those oscillations decay, and it eventually comes to a rest. The same thing happens for the charge on the capacitor. It initially oscillates, those oscillations get smaller as time evolves. So, for example, if I was to plot for the LRC circuit, let me do this. Let's do it this way. If this is T and this is the charge Q, if we start with an uncharged capacitor, we expect that initially Q will equal to 0, of course, if it's uncharged. But then we know after a long time, we'll reach this Q equilibrium. And so we can kind of indicate where that is. It's somewhere over here. This is Q equilibrium is CV naught. Okay, and so what we know is this thing will oscillate about that equilibrium, and those oscillations will decay away. Okay, so you're going to build the LRC circuit in lab 4. Again, you're not going to be given like a physical switch, but we can use the square wave output of a function generator to simulate the switch being flipped up and down. So every time you flip the switch, you expect to see a series of damped oscillations. Yep.
Is this behavior specific to AC circuit or?
This is not an AC circuit. This is the only voltage that we're going to provide is the DC constant voltage. We're just going to turn that voltage off and on. So it's like we're taking the battery in and out of the circuit. Yeah. Again, we will talk about AC circuits. It's the next thing we'll talk about after we finish this stuff up. So what I want to do is I want to write down, I'm just going to give you the solution for the charge on the capacitor as a function of time. and then we'll see what that looks like. So if Q equals 0 at T equals 0, so if that's our initial condition, then for an underdamped LRC circuit, and underdamped, remember, means that R is small. So we could arbitrarily make our circuit as underdamped as we want by just keeping R as smaller and smaller and smaller. So the yeah, that's right. So the solution for the charge on the capacitor as a function of time is, okay, so let's see, Q of T is equal to, well, what we know is after a long time, this thing must be equal to C times V naught. Okay. So we'll have C V naught times 1, and that's going to be our equilibrium after a long time. I'm going to add something on here that will, after a long time, go to 0. So we have a oscillation here. So we're going to have some kind of trig function. Should I use cosine or sine for this oscillation? Why cosine? Yeah, so it starts at a minimum. What we're going to do is we're going to have a 1, and then you're right, it is a cosine. We're going to do a minus cos. And then be some frequency, which I'm going to call omega 1 times t. So then if I put t equals 0 here, what I would get is cos of 0, which is 1, and then we'd have a 1 minus 1, which is 0, and so that corresponds to that point. Okay, what about this decay? What does this decay look like? What is this dashed blue line, which just touches, oh, yeah, it looks like a decaying exponential, right? And there's the same sort of curve on the underside here. So this part goes as e to the minus t over tau. And so that's what we're going to include in front of our cosine. So we would have e to the minus, actually, I'm not going to write this as tau. That's correct, but I'm going to write it in a different way. It's still going to be this exponential decay, but I'm going to write it as this quantity gamma over 2 times t. Okay, so we'll put in this minus gamma, whoops, Greek letter gamma over 2 times t. All right, and so I'm going to tell you what these parameters are equal to. So we've introduced 2 new quantities. One is gamma, which controls how quickly our oscillations decay away. And the other is this omega 1, which is going to be related, well, it is the frequency of these oscillations. Okay, so this is where gamma is equal to R over L, and omega 1 is equal to, I have to introduce another quantity, omega naught, and omega naught is equal to 1 over root LC. And so it's not obvious at all why these quantities have this form, but I'm just telling you the solution. So, but take a look at this. Omega naught depends on L and C. So those are just components in your circuit. You get to choose those. So you know omega naught. And then gamma is R over L. Again, just components in your circuit that you get to choose. So you can calculate gamma, if you know omega naught and gamma, you know omega one, and then you know everything that's in here. Okay, so what you're gonna measure is not directly the charge on the capacitor. We'll measure the voltage across the resistor, which is I times R. So if I want to know the current, what I would have to do is take the derivative of this charge, and that's exactly what we're going to do. So in lab number 4, you will measure the voltage across the resistor, which is VR is I times R. Okay, so that means we need to evaluate I is dq dt. And let's see if I can get that on the screen. You can already see that it's going to be a bit of a mess, right? Because when I do the derivative, I have in the second term a product of two functions that both depend on time. And so that means we have to use the product rule. What about the first term? What's going to happen when I take the derivative? What happens to the first term? Yeah. It's just a constant, so it vanishes. All right, so we ignore the 1, then we're going to get a minus. And then we have the derivative of the exponential. So that brings out a minus gamma over 2. That cancels the original minus sign. Then we get the exponential back again. And then we have to carry the cosine term along, our factor. And then we have to do the other part of the derivative. Let's see, we're going to get a minus times the exponential. So we would have minus e to the minus gamma over 2 times t. And then we have the derivative of the cosine. What's the derivative of the cos? It's going to be minus sine. And we'll get a factor of omega 1 coming out. So what we have to do is we have to change our minus sign to a plus. We get an omega 1. And then the cosine becomes a sine. Okay. And so you could see that this is pretty complicated. And we want to look for ways that we could simplify this. So if we restrict ourselves to very, very underdamped systems, then let's see what that would mean. We have two terms. One has a gamma in front of it, and one has an omega 1. If we're really, really underdamped, then R is small. So that means gamma is a small number. Gamma's in here as well, so that's also small. But it also has this omega naught in here. So we have some number minus a small number. We would just ignore the small number. And over here, gamma is just small. So because this has a coefficient of gamma out front, this first term is small when we have a really underdamped system. So for very underdamped circuits, R is small, which means that gamma is small. Therefore, we can ignore the first term in I compared to the second term. Okay. So if we do that, actually, before we do that, notice also that omega 1 is equal to the square root of omega naught squared minus gamma over 2 squared. But this would be approximately just equal to omega naught when r slash, well, r gamma small. Okay, so if we do those two things, I'm going to rewrite this current where we're going to say the first term I don't care about. I'm going to keep only the second term, and omega 1 is basically omega naught. And so what we end up with is I is approximately omega naught. Oh, sorry, I forgot something. What did I forget here when I took my derivative? Can anyone see? I took the derivative of the stuff in the brackets, but what did I forget? The CV naught. Yeah, that's right. So what I'll do is I'll say over here, if I divide by that CV naught, this is what my current would be too. Okay, yeah, so I just forgot that constant. So let's put that constant back in. I'm going to have omega 1, which is approximately omega 0. And then we're going to multiply by CV naught. And then we have our exponential. And then we have our cosine. And I'll again change the omega 1 to omega naught. And so now all we have to remember is that gamma is equal to, it was R over L, right? Yes, gamma is R over L. And omega naught is equal to 1 over square root of LC.
Wouldn't that be sine there?
Oh, yeah, you're right, because we took the derivative, right? Thank you. You are absolutely right.
Is it also gamma naught times t, or is it just still a function? Gamma naught
Gamma naught.
in the sign.
Yeah, no, this is the sign of the product of omega naught and t.
Okay.
Yeah. Okay, so therefore the voltage across the resistor is VR is equal to I times R. All we have to do is just put in a factor of R. So we would get omega naught RC V naught e to the minus gamma over 2 times t. It's the sine function of omega naught times t. And this is what you're going to measure in the first part of lab 4. Lab number 4, day 1. Okay, the sorts of things that you'll be interested in, let's plot what that would look like. So here's T, and here's the voltage across the resistor. Now, if we go to T equals 0, we'll get the sine of 0, which is 0. So this is going to start here. If I go to, here, I'll make that red, I think. If I go to a very long time, I'm going to get e to the minus something times t. But if t is large, we'd have e to the minus a large number. It's going to go to 0. So eventually we'll end up here. So we're going to start at 0, and we're going to end at 0 for the voltage across the resistor. And then obviously there's going to be some oscillations because of the sine function, and the amplitude is going to be exponentially decaying because of e to the minus gamma over 2 times t. And so what that ends up looking like is something like this. Okay, and we'll put in our little envelope functions that just kiss the peaks and minima. And so these go as e to the minus gamma over 2 times t. And let me label here the period. The period is the time to complete one full oscillation. So what you'll measure in the lab is the times of these peaks and the voltages of these peaks. So this would be like, how do I want to write it? This will be at time t1, we have voltage v1. And at time, I'm going to jump to t3 for a second. We're going to have voltage v2, v3. And this will be time t5 and voltage v5. And then we can go down to these ones over here and say, well, we also have these negative ones. And so this will be time t2. Here's voltage v2. Here's time t3. This would be a 4, v4. T4, v4. And here's T6, V6. What you're going to do is you're going to make a plot of the absolute value of the voltages, say J, versus TJ. And we're going to use the data to measure gamma. So the reason I chose an absolute value is because these will all obviously be negative voltages. But if I took the absolute value, that's like flipping this, inverting this up. And if you did that, your plot would have these minima would just fill in the space between maxima. Okay, the other thing you'll measure is you will measure the period t. And so let's remember, omega naught is angular frequency. That's 2 pi over t. And so that means t is 2 pi over omega naught. But remember, the way we defined omega naught, it was 1 over the square root of LC. It's over here. Omega naught is determined by the inductance and capacitance in your circuit. And so this would be equal to 2 pi root LC. So gamma is R over L. And so you're going to measure its value and then compare it to what you expect. T is determined by the inductance and capacitance. So you'll calculate an expected value and then compare that to your measurement. Yeah.
When you have the expected value and the measured value, and move uncertainties.
Yeah. You would just see if their ranges of uncertainty overlap, right? So
at the same time.
I don't know what you mean by at the same time, but if you had like I don't know, let's say you did a let's say you measured gamma. And so this is your gamma measured was right here, and then your uncertainty range was something like this. So this would be gamma measured minus delta gamma measured, and then over here you'd have gamma measured plus delta gamma measured, right? And then you also have a calculated value, and maybe your calculated value sits here, gamma calculated. But you're going to calculate it from R and C also have uncertainties. And so you'd have like some range of values for your calculated gamma. And so this would be gamma calculated plus delta gamma calculated. And over here, we'd have gamma calculated minus delta gamma calculated. And if you have overlap between your ranges of uncertainty, you would say that your calculated or your expected and your measured values agree. But if this red one was, say, shifted over here so that there was no overlap, then you would say they're, you know, they don't agree with one another. Yeah.
Is there a threshold, like minimum threshold for the small resistor? We're gonna use a small resistor for the LAD4, right?
Yeah, it actually won't be that small. It turns out that it has to be small compared to the gamma, which is R over L, has to be small compared to the omega naught. So we'll easily satisfy that condition. Yeah, yeah. But there is a minimum value, right? You could put no resistor in there, and then what you're gonna end up having is some finite resistance in your wires, and that will determine the value of gamma. Okay, so good. So we have about 15 minutes left, and so what I want to do is I want to start the next topic. So the next topic will be an analysis of the frequency response of an RC circuit. And so another way to say that is, if I had an RC circuit, how does I vary with the frequency? So far, what we've been talking about with the charging and discharging capacitor and even these damped oscillations in the LRC circuit is, how do things vary as we let time go by? But what I have in the lab is I have this function generator that has a frequency knob, and I can drive my circuits with a sine wave input, and I can change the frequency of that sine wave. And so how does the behavior of my circuit change as I mess around with that frequency knob?
By IG.
Yep. Yep. So let's draw an RC circuit. So here's a capacitor in series with a resistor. And what we'll do, we've drawn the circuit before. The only difference is we had a battery here before and maybe a switch. Now we have our function generator. So this is our function generator circuit symbol. And what we're going to do is we're going to have that function generator output a sine wave. And the sine wave is going to have some amplitude and some frequency, and we can adjust both of those things. Okay. What we could do is maybe we want to measure the voltage across our resistor, and we do that with an oscilloscope. Here is going to be the current I in our circuit. This is C, this is R, and we can just do an analysis of, it's just a one loop circuit. We can just keep track of all the changes in voltages around that loop, and we could analyze it. And that's in fact exactly what we're going to do. Before we do that, I just want to make sure that we're all comfortable with interpreting sinusoidal functions from the plot. So what is the meaning of all these things in this V naught and this omega in our function generator output? So this is going to be V naught sine omega t. And so our sine wave looks something like this. A little bit higher, there we go, something like that anyways. So what we'll have is some maximum value and a minimum value that's equal to minus that maximum. And those min and max are determined by the amplitude. So this is going to be plus V naught is the maximum, and the minimum is minus V naught. So V naught is called the amplitude of our sine wave. Then the time it takes for our sine wave to complete one full cycle is the period. And so that's something we could measure on the oscilloscope. So T is the period, or the time to complete one full cycle. The frequency F is equal to 1 over T. And so that's the knob that you have on your function generator, okay? So these you can tune with the function generator knobs. And then finally we have, so this is frequency. The other thing we have is angular frequency omega. And so that's 2 pi times F, which is the same thing as 2 pi divided by the period. And so this is angular frequency. So the things that you could actually measure using an oscilloscope are the amplitude and the period. But once you have the period, then you can calculate frequency or angular frequency, whatever you need. Okay. So in order to analyze this problem, let's make a couple of observations. So observations from part 4 of lab 2. So you just did lab 2 last week, and in that last part, what we had is exactly the circuit that we drew here. You had your function generator, you had a capacitor and a resistor. The resistor, I think, was 10K. The capacitor, I forget what it was, but it's some value, and you set the frequency to 16 kilohertz. I think the capacitor was probably a nanofarad. And what you saw on the oscilloscope was that if you looked at the output of the generator and the output, or the voltage across the capacitor and the voltage across the resistor all at the same time, we had to use math menu to do that. Nevertheless, we did it. We saw that the peaks were all at different times, or same, like the zero crossings were at different times, or the minima were at different times. So there was some phase shift between the various quantities that we were trying to look at. In addition to the phase shift, if we looked at the period of every signal, those were all the same. So the frequency of the voltages across the capacitor and resistor was the same as the frequency as that was output by the generator, but the phases were different, okay? The voltage across the resistor is I times R. R is just a constant. So what that means is that if the voltage across the resistor had a phase shift, then so did the current. So those are the observations that I want to write down. So the current oscillates sinusoidally at the same frequency as Vn, or the signal provided by the function generator. The current was out of phase with Vn. And the other thing we saw is that the function generator had some maximum voltage. If you had the amplitude knob turned to maximum, then the function generator would peak at 10 volts. But the voltage across the resistor and the capacitor didn't reach that 10 volts. But if you were to change the frequency knob, you could make the heights of the peaks for the capacitor and resistor change with frequency. So the amplitude of the current depends on the frequency or the angular frequency omega. And so what we're going to do in order to capture all these observations is we're going to assume that the current in the RC circuit is of the form. Okay, so we'll have, I'm going to use little I for this current. Typically, I'll try to use lowercase letters for AC signals, something that oscillates sinusoidally, and I'll use uppercase characters for quantities that are driven by DC voltages. So we're going to have an amplitude, which I'm going to call I naught. And we said that that amplitude is going to depend on the frequency. So I'm just going to emphasize that by saying that I naught is a function of the frequency omega. We said that the current is going to oscillate sinusoidally. And so what we'll do is we'll say, okay, there'll be a sine function. It has a frequency, the same frequency as Vn. So if Vn is at frequency omega, or angular frequency omega, then so is the current. And then the last thing is that the current was out of phase with the input voltage. And so I got to put in a phase factor. If you, I don't know, had the opportunity to change the frequency on your function generator when you were doing part 4 of the last lab, you would have saw that not only does the amplitude change with frequency, but so does that phase shift. So this phase is frequency dependent as well. So this is a frequency dependent amplitude, and this is a frequency dependent phase. And our goal is to find expressions for I naught of omega and phi of omega. Okay, so I'll just set up the problem that we're going to try to solve, and then we'll tackle that. I guess we'll tackle it, it won't be Monday because there's no classes Monday, it'll be Wednesday of next week. So let's do a Kirchhoff loop rule of the series RC circuit. Okay, so it's over here. So if we did the loop starting here, we'd cross the function generator, so we'd get the voltage Vn being supplied by that generator. And then we have some voltage drop across the capacitor and the resistor. So the loop rule says we would get Vn minus the voltage across the capacitor. The voltage across the capacitor is Q over C. I think C is Q divided by V. So V is Q divided by C. Yeah, that's right. Okay. And then we would have minus IR is the voltage across the resistor. And then we'd be back at our starting point, and that would be 0. Okay. So the problem we have here, we've seen this problem before, is we have charge and we have current. And so I want to have a differential equation in one of those variables. So to make a differential equation in I, we're going to take the derivative of, let's call this star. Okay, so I'd have dvn dt. Previously, if we did a derivative like this and we were using a battery, the battery output is constant, so we would get 0. But now we have a sine wave, and that's not a constant. So then we'd have -1 over c, and then we have the derivative of q, which is the current. And then we'd have minus r times di dt, and that would have to be equal, and the goal is to solve for I of t. And we'll try to do that. What we're going to find is that it's actually quite a bit of work to solve this equation. And so because of that, we are going to develop new techniques to solve problems like this that will allow us to avoid actually solving differential equations directly. Okay, so that's what we'll start with next week. All right. We'll see you in the lab tomorrow.
Yeah.